Okay, this video is going to be a reminder about how to do problems where you have a linear mass density. So for example, you've got a rod, it's got a length of L and a mass of M, and they're going to give you some sort of linear mass density. For example, they might say it's B times x squared. That's going to be your linear mass density, which means starting from wherever we are over here, if this is our x equals 0 point, it's going to be getting more and more dense as the length of the rod goes on. So they will often ask you maybe to find the center of mass or the moment of inertia. So let's do both of those. So first of all, let's remember what this lambda means. That's a mass density. So that's going to be the mass per length. But remember, it can also be dm dx. So that is a little bit of mass and a little bit of length. So if you're given this, sometimes it's nice to be able to find the mass in terms of B and L, and that way it's going to come in later on. So one of your first steps is going to be to remember that if you've got this lambda equals dm dx, then you can say that dm is lambda dx. And now if I want to integrate both sides, then I can find the total mass is going to be the integral, and this is our lambda right there, of bx squared dx. And we want to integrate that from 0 to L, all across the length of the rod. And then this is a pretty easy integral to do. So we're going to get the mass is b over 3. I'll just skip a step, b over 3 L cubed. You can make that integral, that's pretty easy to do. So this is just something to kind of keep in your back pocket when we are figuring some other things out. So let's move down here and let's figure out what the x center of mass of this thing is going to be. So remember, if we're finding x center of mass, that's going to be 1 over m times the integral of x dm. Okay, so that's just our basic center of mass formula right here, 1 over m integral of x dm. If you remember, just up here, if you just have like a bunch of little objects, like an object, an object, an object, an object, and so forth, then your x center of mass is going to be m1 x1 plus m2 x2 plus m3 x3, all that kind of stuff, whatever it is, divided by m1 plus m2 plus m3 and so on. So that's if you just have individual things. If you've got a continuous piece of mass, then it's going to look like this formula here. So what are we going to do with this? Well, we remember that, where are we getting this from? So we can have x dm. Remember up here, dm is lambda dx. So I'm going to change this into 1 over m integral x, and once again, dm is lambda dx, but remember lambda is also bx squared. So this is going to be 1 over m integral of x and bx squared dx, right? And we still want to integrate this from 0 to L, Good, so this is a pretty easy integral to do. I'm just going to pull the b out, b over m integral x cubed dx. That's pretty easy. B over m, and we get x to the 4th over 4 integrated from 0 to L. So that's going to be b over m times L to the 4th over L. Just like that. And so now what we're going to do is we're going to take this expression for mass and then put it in for our mass down there so that we can get rid of m and we can just have things in terms of L. Oops, this is a 4 in the bottom, not an L. There we go. That confused me for a sec. So that's a 4 in the bottom. And so let's substitute in this for the m down there. So this is going to be b over 3 L cubed, and then L to the 4th over 4. Good. And then we can just rearrange everything over here. The b's are going to cancel. The 3 is going to come up to the top. 3 L's here are going to cancel with 1 L there. So we end up with just 3/4 L. And this is good, and this is our x-com. And we want our units to be in terms of length units. So if this would have come out as L cubed or L squared or something over L, that would have been weird, but this is fine. And the fact that it's 3/4 L makes a little bit of sense because it's getting more dense as it's going this way. So we know that the center of mass wasn't going to be in the middle. It was going to be somewhere over here because it's more dense on this side than on this side. Okay, so now let's do the other problem that they sometimes pop out at you, which is finding the moment of inertia. So just remembering our formula for moment of inertia is going to be integral of r squared dm. And that's for a continuous piece of something. And once again, if you just have a pivot point and an object that's over here, then our moment of inertia is going to be m times r squared. So whatever this mass is and that radius, that's for like a one object. But if you've got a continuous realm of objects, then it's like this. So this is going to be pretty similar. We're going to have, we need our dm over here, which once again is lambda dx. And then I'm just going to switch variables from r to x. So this is going to be integral of x squared and then lambda dx, because that's what dm is. dm is lambda dx, if you remember from way back up here. dm is lambda dx. And so now, once again, we're integrating from 0 to L. So this is going to be integral 0 to L of x squared times bx squared dx. Lambda, once again, is bx squared, so don't forget about that. So that's that. And then we're just going to do the integral, which is pretty easy. So we have b integral of 0 to L of x to the 4th dx. So of course that's going to give us b L to the 5th over 5. Yes, so it's to the 5th power this time. And then once again, we're going to come back and substitute in, oh actually sorry, this time we're going to need b in terms of m because we want m in the final answer here. So when we look back up here, we've got m is b over 3 times L cubed. So let's just write that down. M, here we go, equals b over 3 times L cubed. Let's find out b in terms of m for this because we want a mass in our moment of inertia formula over here. So this is going to turn into b equals 3m over L cubed. That makes sense. So now we're going to stick that in for a b up there. So then we're going to get our moment of inertia is 3m over L cubed times L to the 5th over 5. And then that's going to be 3/5 I equals 3/5 m L squared. And these are the kind of units that we want to have on here. We want to have something times ml squared. Remember, all of our moments of inertia are going to be something times ml squared. Whether it's a hoop, which is just ml squared, whether it's a disk, 1/2 ml squared, and so forth, but it's always something times ml squared. So this one's 3/5 times ml squared. And I can't say that that intuitively makes a lot of sense for me, where I'm thinking we're pivoting around this point. I guess I should have mentioned that before. We're pivoting around this point, and the moment of inertia is 3/5 ml squared. Okay, sure, if you want to. It doesn't necessarily have an intuitive sense to me. So this is just something to keep in mind, and I've seen problems just exactly like this. Just one other thing to point out, you could do a similar problem if lambda was b times x instead of bx cubed. Sometimes they could give you something weird where they're going to say lambda is, I don't know, some exponential thing like e to the x times x or something like that. I don't know. They're going to give you something interesting, but you can always take derivatives and figure out what is dm dx and so forth. These are probably the most common that you're going to see. Okay.